Logic statements and quantifiers. In a logic, a quantifier is a way to state that a certain number of elements fulfill some criteria. For example, every natural number has another natural number larger than it. Two basic kinds of quantifier used in predicate logic are universal and existential quantifiers. Statements. A statement is defined as a declarative sentence that is either true or false, but not both simultaneously. Example: the earth revolves around the sun. The sun revolves around the earth. 1 plus 2 equals 3. How do you spell your name? This sentence is false. Alin is not a good student. So, example of negations. The sentence, Max has a car, is a statement. The negation of the statement is, Max does not have a car. The negation of a true statement is false. The negation of a false statement is true. So, example, write the negation of each statement. The earth revolves around the sun. So, there are only two possible scenarios here. Either it does or it doesn't. So, the negation of the earth revolves around the sun is the earth does not revolve around the sun. So, this is our solution. The earth does not revolve around the sun. We proceed to the truth table's equivalent statements and tautologies. The truth table shows how the truth or falsity of a compound statement depends on the truth or falsity of means that P and Q equivalent. And we covered two of what will eventually be 5 basic truth tables whose value will allow us to tackle many more complex logical statements. True only when both P and Q are true. False only when both P and Q are false. So, example, if this is true, statement, the ball is red, then this is false. The negation, the ball is not red. If a compound statement is made up of n simple statements, there will need to be 2 rows in the corresponding truth tables. So, we have an example in the box. So, there are 3 simple statements that we need. The conditional and biconditional. We have an example in the box about the conditional and biconditional. A biconditional statement is a combination of a conditional statement and its converse written in F and only F form. 2 line segments are congruent if and only if they are of equal length. A biconditional is true if and only if both the conditional are true. So, we proceed to the conditional and related statement. A conditional statement is false if hypothesis is true and the conclusion false. If we rearrange a conditional statement or change part of it, then we have what is called related conditional. So, converse, inverse, and contrapositive. Conditional statement. P implies Q if P then Q. Converse. Q implies P if Q then P or the reverse. Inverse. Not P implies not Q if not P then not Q sign change. Contrapositive. Not Q implies not P if not Q then not P or the reverse and sign change. Example. Given the conditional statement, if I live in Wisconsin, then I shovel snow. So we will find the converse. So we're going to change order of the implication. The inverse change sign, we're going to negate each component statements. So the last, the contrapositive, reverse order change sign. So instead of if I live in Wisconsin, then I shovel snow, it makes if I shovel snow, then I live in Wisconsin. Then second, if I live in Wisconsin, then I shovel snow. So it would be if I don't live in Wisconsin, then I don't shovel snow. So, proceed to symbolic arguments. Symbolic arguments consist of a set of premises and conclusion. It is called a symbolic argument because we generally write it in symbolic form to determine its validity. An argument is invalid or fallacy when the conclusion does not necessarily follow from given set of premise. Arguments. When someone makes a sequence of statements and draws some conclusion from them, he or she presenting an argument. An argument consists of two components, the initial statements or hypothesis or premises and the final statement of conclusion. Types of arguments. First, an inductive argument uses a collection of specific examples as its premises and uses them to propose a general conclusion. Specific to general. Second, a deductive argument uses a collection of general statements as its premises and uses them to propose a specific situation as the conclusion from general to specific. So, we have an example of symbolic form. We proceed to arguments and Euler diagram. Argument and Euler diagrams. An argument can be classified as either valid or invalid. A valid argument occurs in situations where if the premises are true, then the conclusion must also be true. Using an Euler diagram to analyze this argument, draw a circle to contain all objects that have flares. Euler diagram. Used for arguments that have quantified statements to determine validity. First, A is inside of the diagram. Second, no A are B. Second one is A and are B. Third, some A are B. And the last, some A are not B. So this time we're talking something and inside the hard. How to use Euler diagrams. Make an Euler diagrams for the first premise. Make an Euler diagram for the second premise on top of the one for the first premise. The argument is valid if the only if every possible diagram illustrates the conclusion of the argument. If there is even one possible diagram that contradicts, the conclusion is not true in every case. So the argument is invalid. Example, use Euler diagram to determine whether the following arguments is valid or invalid. All people who arrive late cannot perform. So, the first thing we need to do is to make Euler diagram for the first premise. It should look like this. Circle. The circle that the people that arrive late is located inside the circle of those who cannot perform. And now, I have an Euler diagram for second premise. All people cannot perform are ineligible for scholarship. So, this circle, so a valid Euler diagram, this circle that shows that the argument indeed valid.